A rational function is a function that's more or less made up of two polynomials divided by one divided by another one. I've listed three here. This is on the handout that I've given you, these three. Here's three examples of what are called rational functions. Ratio is the name there, ratio, so it's a ratio of polynomial functions. Two polynomial functions divided by one another. And you can have very simple polynomials, x minus 2 divided by x minus 3. 5, you just have a constant divided by a polynomial. Now, and they can get more complicated, of course. We won't get too carried away, but on the ones we do. But that's what rational functions are. So we've got division, and that can lead to a lot of things. But so first thing that I want us to note here are, I call them excluded input values, excluded values. Yeah, because when you start dividing by a polynomial, we know that the denominator can't be 0. So excluded values here are values of x, the input value, that make the denominator 0, equal 0. One way to put it. And so on our first one here, the first one, we would have to say the excluded value there is 3, right? X could not be 3. So 3 would be excluded value. Now what that means is, if it asks for the domain then, I forgot to put my numbers, 1, 2, 3. So the domain on number 1, well, the domain is the input values, what x can be, and so what can x be in number 1? Anything except 3, right? So the domain, that's probably the best way to put it, is it's all x's except, or all real numbers except x can't be 3. What are the excluded values for number 2? What's the domain? All right, so in number 2, excluded there, well, it's values that make the denominator equal 0, and so if you can't see it, just set the denominator equal to 0, and that's going to be the excluded value, because your denominator can't be equal to 0. You try to divide by 0 on a calculator, and it tells you error, or something like that. Yeah, you just can't have the denominator equal 0, and so add 7 divided by 4, that would be 7 fourths. That would be the excluded value, and so that means the domain would be all real numbers except 7 fourths. Something like that. And then number 3, what would be the domain on that?
I'll have 2 probably.
Yeah, since you've got the denominator is x squared plus 4x minus 12, that can't equal 0, and so yeah, if we solve that out, factor negative 12, 6 and 2 is a 4 in the middle. So it'd be plus 6 and minus 2, so x could not be, that would be negative 6, and that would be positive 2. And so my domain, everything except those. So if it asks for a domain on these rational functions, that's what we're looking at, just setting the denominator equal to 0 and excluding those. All right, well, as you might guess, the graph then gets a little complicated when we try to go graphing these. So let's try. Any questions on that? So the first one we're going to look at is f of x equals 2x plus 1 divided by x minus 1 here on the handout. All right, so let's just start by doing something we know, plotting points. So the y value is just going to be the 2x plus 1 divided by x minus 1. So we plug in -3. Well, we have -6 plus 1 divided by -3 minus 1. So you got -5 over -4. 5 fourths, or 1.25. -2, that would give me -4 plus 1 over -2 minus 1. That's a -3 over -3, that's a positive 1. -1, -2 plus 1 over -1 minus 1, so that's a -1 over -2, positive 1/2. 0, 1 over -1 is -1. And what about 1? Well, if I do 1, it would be 2 plus 1 over 1 minus 1. That's what we're just talking about, isn't it? You can't have divided by 0, and so, yeah, there's nothing happening at 1. And then 2 and 3, what do we get there? 4 plus 1 would be 5 over 1, that's 5. And then 3, we get 7 over 2. 7 halves or 3 1/2. So I've got place here. Try to reproduce it. Putting those on, so -3, 1 1/4, oops, 1.5, 5, 10, 15, 20, these are 2s. So -3, I'm at 1 1/4. -2, I'm at -1, positive 1, sorry. -1, I'm at 1/2. 0, I'm at -1. Two, I'm at 5. And 3, I'm at 3 1/2. Okay, so that, yeah, trying to make a little sense out of that. Well, what I said is, let's look at points, some more points around those, and I've already computed these in this table. I've got x is 0.5, then the y is -4, 0.9, the x is -28. So let's just look at those two first of all. So these are values around our excluded value x equals 1. Right, because that's the excluded value here is x equals 1. So at 0.5, I've got -4. So here's 1. So at 0.5, I'm at -4. And then at 0.9, 0.9, I'm at -28. So real close to 1. I'm way down here at, maybe even off the, well, got it down to -25, so it is just a little bit off what I provided there, but it's -28. Now if I look at the other side of 1.1 and 1.5, I've got values there at 32 and positive 32 and positive 8. So at 1.1, it's way up here at 32. So at 1.1, it's 32. And then at 1.5, it's 8. Here. Probably looks a little better than mine, but all right. Well, let's just connect these dots. All right, so I've got, this is kind of going here to here and then down here. And then these points follow the dots up to there. Well, hopefully we can see there that at this +1 value, let's just draw in a little dotted line there. because x can't be equal to 1. And so I'm not going to cross that. I mean, that line is technically not there, but I'm not going to be able to cross that line because x can't be equal to 1. However, what I see is as I get closer and closer to x equals 1, these values, well, they're headed down, negative infinity, if you want to say it that way. As I approach it on this side, these values are getting larger and larger. They're going to infinity, positive infinity. This is what's known, what we have at x equals 1 is what's known as a vertical asymptote. Vertical asymptote. So the graph is said to have a vertical asymptote. I guess I stated it a little differently on the paper, but you get the idea. Now, why did I have a vertical asymptote there? Well, it was because what was x equals 1? It was the excluded value. So, in general, the graphs of rational functions will have a vertical asymptote so we'll have a vertical asymptote when, so it's an excluded value, but that's when denominator equals 0, okay? So that's how we'll find these vertical asymptotes. That's the first thing we're going to do here is find asymptotes, the first of which is the vertical asymptotes. The vertical asymptote is going to be when the denominator equals 0 in general. There are some exceptions there, but all right. Now, flip over to the second side, the back side there. So we've still got the same function. Now let's look at the end behavior. Well, the end behavior is the values that occur out with x's, positive large x's or negative x's out this way. And so what on the table I've already got there, you can check on these, but go ahead and I've gone ahead and computed at x is negative 10, the y is 1.7, at x is negative 6, y is 1.57, and at x is negative 4, we've got y is 1.4. So I'm looking at these values out here, all the way out to negative 10 is my first one I've got on the table there. So I'm looking at values out on the end of this graph. And so at negative 10, I'm at positive 1.7. And so let's say there's, that's a little high. Say there's 2. So at positive 1.7 is where I'm at negative 10. 1.57 at negative 6. And negative 4 is 1.4. So I'm not going anywhere fast. In other words, as I go out on the ends, connect the dots, I'm going out here like that. Well, if I go on the other side and do positive 4, positive 6, and positive 10, sort of the same thing happens. 3 for y, 2.6 at 6, and then 2.3 at 10. So I put those on here. 4 I'm at 3, 6 I'm at 2.6, and 10 I'm at 2.3. Yeah, those also are not going anywhere fast, you might say. What we can say, here's what we're going to say, how we're going to say it. What we're going to say is those are leveling off. On the ends, it looks like the graph is leveling off, okay? And specifically, if you think about it, if you draw a horizontal dotted line, they're leveling off at y equals 2. Well, in this particular case, that y equals 2, notice there I've got a horizontal dotted line, so guess what it's called? That's a horizontal asymptote. Now, it's a little different as far as finding where our horizontal asymptote, because we don't want to have to do tables like this every time. So we know how to find those vertical asymptotes. So why is it y equals 2? Well, if you look at, for horizontal asymptotes, here's what we're going to look at. We're going to look at y equals a over b, where a and b are kind of, the way I'm going to approach it is, those are going to be matching terms. So b is going to be the leading term of the denominator, which in this case is x. And then a is going to be the leading term on the top, which is 2x. And so if I set y equals that a over b, I'm calling it, look at what I get. 2x divided by x, what does that give me? 2. That just gives me 2. And that's not by coincidence, okay? So that's how we're going to find the horizontal asymptote, is we're going to use this, or the way I do it is use y equals a over b. If we've got, now the degrees, we need the degrees to be matching there, because you want the x's to cancel out. All right? So, in general, for a rational function that has the degree of the numerator equal to the degree of the denominator, so if the degree numerator equals degree denominator, the horizontal asymptote is at y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. Now we can make a little bit of provision for that if we need to. So I've got a and b. So using those two pieces, we'll pick up on this next time, but all right, so a, f of x equals 7 minus x over 3x plus 5. So I'm asking for the asymptotes. Well, we've got two, vertical and horizontal. Find the vertical asymptote. We just went through it. How do we find it? Denominator equals 0. So in this case, we go 3x plus 5 equals 0. So subtract 5 divided by 3. That's our vertical asymptote. Easy as that. Horizontal, how do I do that? Well, if the degrees are equal, you do y equals a over b. Now, in this particular case, what's my a, what's my b?
A is x, b is 3x.
A is negative x, isn't it?
Oh, yeah.
And then b is 3x, and so the x's cancel, so that's negative 1, negative 1/3. So y equals negative 1/3. That's my horizontal asymptote. Is that okay? Now I have b here because it's got a little bit of a twist to it. F of x equals 7 over x squared minus 2x minus 3. All right, so my vertical asymptote, denominator equals 0, so that's going to give me 2. Because you got x, that one factors as x minus 3 and x plus 1. So you've got, set that equal to 0, you got x is 3. That equal to 0, so you've got two vertical asymptotes in that case. And then the horizontal asymptote, well, that's where we have, make a little bit of provision here for that. To do this A over B, the degrees have to be matching. Well, the degree of the denominator is x squared. Does the top have an x squared? No. However, I could fill that in with 0x squared, couldn't I? Yeah, to make these match, I have to do the top is 0x squared because it doesn't have an x squared, so it has to be, we have to going to say it's 0x squared. Well, yeah, your x squareds cancel. What does that leave you? 0. Y equals 0. So the horizontal asymptote, in that case, yeah, you're going to get a y equals 0 horizontal asymptote. We'll do some more on next time.